Hi everyone and welcome to this next lecture of the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we studied about bagging, which is an approach to an ensembling strategy for decision trees and allows us to combine multiple decision trees and aggregate them to obtain better precisions. It also involved the act of bootstrapping, wherein we generated various data sets by sampling again and again with replacement, and we also saw why bagging works due to the out of bag error estimate that can be obtained. So in today's lecture we will go ahead and look at other concepts used in ensembling such as boosting as well as random forests. So let us go ahead and get started. So the first topic for today is random forests, and this is a slight variation of the bagging approach. And this approach mainly tries to address the little bit of overfitting that can still occur with bagging. So what happens in a random forest and why is it called a random forest? So already some thoughts may be coming to your mind, right, and I will try to explain what these words mean. Forest of course is referring to the collection of decision trees that is used for the ensemble here. So that is the origin of the word forest, and random is actually referring to the subset of features selected randomly which is actually used to grow the tree at every stage when we do recursive binary splitting. So let us go ahead and write these down to cement our concepts. So a random forest model adopts a similar approach as bagging by combining bootstrap and aggregation. Okay, so you are combining bootstrap and aggregation. The word random refers to the fact that at each recursive binary splitting iteration, while growing the tree, a random subsample of features is used from the set of available features to decide the best feature cut point combination. Okay. So let us try to understand this. So in a random forest you are still doing bagging. So and bagging, as you know, is bootstrap and aggregating. Bootstrap means you are generating samples of data with replacement. So if your original data set has n points, each bootstrap data set will also have n points which have been generated by sampling with replacement, and aggregation means that you are combining the output of multiple decision trees in a committee based approach. Now the word random it is referring to the fact that at each recursive binary splitting iteration, right. If you remember, to grow a decision tree we adopt a greedy strategy known as recursive binary splitting when we decide the best feature cut point combination, right. So, what is happening is that you are at a particular node and then you are deciding, right, which feature you will use to branch that node, right, because when you branch this node you get two different nodes, right. So, that is where the word binary is coming from. It is recursive because you keep on doing it again and again and again till you have a tree of the desired accuracy, and it is splitting because you are splitting it into two. And if this is jth feature has been selected and S is the cut point, then the left region is xj less than S and xj greater than equal to S is the right region, right. And then we discussed how we can decide which feature we will use and which cut point will be used. So, the choice of the best feature cut point combination, right, is done here with a random subsampling of features. So, it is not that you will use all the features to determine the best jth feature, you will use a subset of features, right. So, the optimal feature j, right, which splits the tree as xj less than S and xj greater than equal to S, right, is determined from a randomly chosen subset of P features of Q features out of the total P number of features, right. And you are doing this to sort of prevent overfitting, right. The model should not always use the same feature to decide. So, over reliance on some feature is a hallmark of overfitting, and that is something we sort of uncovered as early as when we were discussing ridge regression and lasso, wherein we realized that if we do not prevent the weight of a certain feature from becoming too high, the model will start overly relying on that feature, and that is a problem because the model will not generalize well. So, to prevent a feature from becoming very important, right, what we did in lasso ridge was we penalized the sum of squared parameters or the sum of the absolute value of the parameters. Here we are adopting a slightly different strategy. We are saying that we will use a randomly chosen subset of Q features from the P original features, and only out of them we will decide the optimal combination of feature and cut point at every point the tree is being branched. So, that is what is happening here. So, if you want to write it down, so you have P features in total, and in a random forest you randomly select Q of them, right, whenever recursive binary splitting is carried out. To grow the tree. Okay. So, only out of these Q you will select the best feature j every time the tree is being branched. Okay. So, how does this help? Like I said, this helps in over relying, right, on certain specific features, thus making the model more robust and generalizable by preventing overfitting. Okay. So, that is the strategy which is adopted, and as you have seen here, this random subsampling of features has to happen at every node, right, because every node has to be recursively split into 2 more nodes, right. So, once you do it here, you have to do it here as well and here as well till you stop growing the tree. Okay. Now, how do you choose the value of q, right, which is the number of features used to carry out recursive binary splitting over. Okay. So, typically q is taken to be around the square root of p. So, q is approximately the square root of p, right. So, if you had around 30 features, right, in total, then probably q will be 5, right. You will take 5 of those features every time you have to do recursive binary splitting to find the best feature cut point combination. Okay. Now, if instead q is equal to p, then the random forest reduce to regular bagging, right, because in bagging we were also doing bootstrap and aggregation, but we did not say that during recursive binary splitting we will only use a subset of features, we used all the available features to do recursive binary splitting. So, therefore, if q is equal to p, then the random forest models essentially reduce to the regular bagging. However, if you want to do random forest, then typically q is taken to be approximately equal to the square root of the number of features, and that is a good compromise between not using too many features and not losing too many of them. Okay. So, what is the advantage of this, of a random forest? The advantage is that the randomness in choosing features helps decorrelate the trees. So, already the trees were slightly different because every time you had a different data set to train over because of bootstrapping. Now, this is further decorrelating the trees by introducing randomness in not just the data points, but also randomness in the features that will be used at each point in the tree, right. So, this helps decorrelate the trees and thus improves generalizability. By reducing the model variance. Okay. So, model becomes less sensitive to noise because it is forced to look at different features and not just the same set of features each time. So, that helps in preventing overfitting. So, the model can be trained properly, but there is of course a disadvantage, and as you may have guessed, that has to do with the interpretability of the model. So, already when you went from plain decision tree to bagging, that was a problem because you were now generating more and more trees and each of them is trained with different data points. So, if you want to know why a prediction took the value it did, then you have to go through all the trees. Now, this has further complicated it because every tree different set of features would be used at every point, and that makes it much more much less interpretable and more chaotic. Okay. So, the disadvantage is that the model interpretability and the ease of following what happens inside the model increases, the ease of following the model and the interpretability decreases as compared to a decision tree, and further as compared to a regular bagging approach. Alright. So, I hope the discussion of the random forest made sense to you, and one thing to note is, particularly for our core engineering disciplines, random forest models have been really popular. They have been around for about 2 decades, and you can see a number of papers in which these random forest models have proved to be excellent for tabular data. So, definitely this is one of the models that you should be trying out for your data sets, whichever discipline that you belong to. Okay. So, now that we have completed our discussion of bagging and random forests, we will now proceed to the next frontier in ensembling, which is boosting, right. So, the next topic is boosting of decision trees. Okay. And here we are going to study 2 different types of boosting, that is adaptive boosting and gradient boosting. We have already alluded to some of these, but now we will lay threadbare the math behind these concepts. So, let us go ahead and see how this is done. So, boosting is also a committee based approach to improve the performance of decision trees. Okay. But here new trees are grown based on feedback from previous trees. Okay. So, essentially new weak learners, right, which are decision trees for us, are iteratively added to the committee till the desired accuracy is reached. And these trees are grown based on feedback from previous trees, right. So, you try to correct for the errors which have been made by the previous trees. So, you boost the performance of these trees. Now, how do you take feedback from previous trees? So, that can be taken in 2 different ways. So, the first approach is called adaptive boosting. The second is called gradient boosting. Okay. In adaptive boosting you play with the data, right, you see what are the data points which are predicted wrongly and then increase the weights of those points in the loss function, whereas in gradient boosting you use the gradient of the loss function and involve that in the model to improve the model accuracy. Okay. So, that is how feedback from the previously grown trees is incorporated into the newer trees. So, you may have heard of models like ADA boost, right, or that is for adaptive boosting, or in gradient boosting you may have heard of things like XG boost, light gradient boosting machine which is light GBM, or categorical boosting which is cat boost. So, these are the kinds of algorithms we will now try to understand. So, first let us start with adaptive boosting. So, in adaptive boosting you adapt the weights assigned to the data points as you go along in the training of trees, right. So, in adaptive boosting, the weights of the wrongly predicted data points are increased during the training of subsequent trees. Okay. So, that is how you adapt the training process. The weights of the wrongly predicted points are increased during the training of the subsequent trees. So, as you keep on adding new trees to the committee, the newer trees will be able to correct the errors made by the previous trees, and therefore, they will have more superior predictions. So, in particular we are going to study this AdaBoost algorithm, which was introduced in the year 1997, right, and it was first introduced for a binary classification problem. As you remember, in binary classification there are just two classes, class 1 and class 2, and usually they are indicated by a binary number, the target variable y being 0 for class 1 and 1 for class 2, right. So, that is the variable usually what we try to predict, but AdaBoost tries to formulate this a bit differently, right. Instead of the target variable taking the values 0 and 1, here you make them take the values -1 and +1, and that is done in an intelligent way so as to bring in the committee approach directly into the prediction through the sign of the prediction. So, let us see how that is done. So, the true class labels are taken to be -1 for class 1 and +1 for class 2. This is different from what we have been doing in logistic regression or in simple decision trees, the way we have formulated it, but of course this does not make much of a difference, it is just a convenience, right, with which this was formulated. So, the predicted class YB from the bth tree are all combined over all capital B trees to give the final prediction y subscript capital B of x is the sign of the weighted predictions of all the trees, small b going from 1 to capital B, alpha b which is the weight assigned to the bth tree times the prediction of the bth tree. Okay. So, this is the final prediction, right, and these YBs can be either +1 or -1, and like I said, this alpha b is the weight assigned to the bth tree. Okay. And finally, this SGN refers to the sign function, right, and that is very well known in math, right. So, the sign of a number u is +1 if u is greater than equal to 0 or -1 if u is less than 0. So note that this is slightly different from the way the sine function is defined, because in the conventional way when u is equal to 0 then sine is also 0, but because here we have only 2 classes we do not want the prediction to be 0, we always want the prediction to be either +1 or -1, and therefore we do not allow the sine of u to be 0 even if u is equal to 0, right. So you can see here that how very intelligently the aggregated prediction from all the trees is defined using the sum function, right, sine function. So if the sine of this quantity, right, which is the weighted prediction of all the trees is positive, then obviously the +1 votes have won, but if the weighted prediction is a negative number then the -1 votes have won, and therefore the sine of this whole expression here determines the class that you want to predict. So that is how it works. I hope this makes sense. So now what happens, right, this is the prediction once you know what the alpha b's are, but what are these alpha b's and how can we write them down. So the weight for the bth tree is given as alpha b is equal to log of 1 minus epsilon b by epsilon b, which is of course equal to 1 divided by epsilon b minus 1, okay, where epsilon b is a normalized loss function. For the bth tree. Okay. So alpha b depends on the loss function, right, normalized loss function for the bth tree. Let us see if this makes sense, right. Now there can be right a few cases when epsilon b is large, when epsilon b is small. So let us see how these work out. So if epsilon b is small, okay, what does that mean? It means that the tree has a low loss function value. So which means it is more accurate. Now if epsilon b is small, 1 over epsilon b is large and 1 over epsilon b minus 1 is also large, and log of that is also large. So that means alpha b, which equals log of 1 over epsilon b minus 1, will be large. So what you are seeing here is that a more accurate tree has a large weighting fraction, right, and that makes sense. You want to reward or you want to use trees which make less errors, right, and the converse is also true, right. If you took a large value of epsilon b, so if epsilon b is large, the tree has a high loss function value, which means it is less accurate. So if it is less accurate, you do not want to weigh its predictions as much. I mean it is like if you have friends, you will go to the friend who is more likely to give you the right answer, right. So if you look at alpha b, which is log of 1 over epsilon b minus 1, if epsilon b is large, 1 over epsilon b will be small, 1 over epsilon b minus 1 will be small, and the log of that number will also be small. So this weight will be small. So less accurate trees will be weighed less while making the prediction. Okay. So this is how you are able to correct the errors, right, made in the previous trees by changing the weights of the trees, and you give more importance to trees that are more accurate in making their predictions, right. So, at this stage we have not yet defined how epsilon b is calculated, and we have not also defined how each point is weighted, right, because we already said that epsilon b is a normalized loss function. So, obviously the weights of the points also have to come into the picture. Right now we only discussed about the weights of the trees. So, all those things we will take up in the next lecture. I hope you learned something new today. Thank you for joining, and I will see you next time.